Mavuika has been out for a bit of a while, and people have gotten to see her ride around in style. Though, how does this thing actually work? Hello, Count Sacke here, back with another Genshineering video. For those of you who don't know, Genshineering is a series dedicated to analyzing Genshin impact from an engineering perspective. Today, I'll be explaining how Mavuika's motorcycle works, also known as the Flamestrider. I'll be covering energy, energy transfer, the first law of thermodynamics, and heat engines. Hopefully by the end of this video, you'll have a deeper understanding of energy in physics and how gasoline engines work. This is the first video where I take a close look at Mavuika and her motorcycle. I also plan to cover other aspects, such as her drifting skills, how she can skid over water, and trying to figure out how much horsepower it has. But those will have to wait for another video. Be sure to subscribe so that you don't miss out on those. If you don't subscribe now, I'll be nothing more than a temporary heat transfer, dissipated by your phone screen and speakers, soon to be dampened away among the vibrational energy of the air molecules in your room, slowly contributing to the increase of entropy in the universe. While you're at it, like and share the video as it really helps out the channel, and lastly, I have channel memberships where you can get early access to videos or even exclusive behind the scenes footage. Anyway, let's get started. Energy is one of the most fundamental ideas in physics. However, it is also one of the most confusing. While researching this topic, many people, including the infamous Richard Feynman, said that we don't actually know what energy is. All that we do know is that we have well-defined equations for it and that it's conserved. Basically, we know how to use energy to calculate things and make predictions, but if it wasn't already clear enough, what energy isn't an easy thing to describe. At the fundamental level, there are actually only two types of energy: kinetic and potential. Kinetic energy is quite easy to describe. It's the energy of motion. If something is moving, it has kinetic energy. There are two types of motion: translational and rotational motion, so naturally there are two types of kinetic energy: translational and rotational kinetic energy. Potential energy is the energy due to location. It's technically more complicated than that because there has to be something called a conservative force acting on the object at that specific position for it to have potential energy. There are many types of potential energy, some of which include elastic potential energy due to the compression or tension in springs, gravitational potential energy due to height differences in a gravitational field, electric potential energy due to the electric force, and more. This is cool and all, but it only really tells us that all types of energies can be fundamentally sorted into only two classifications. It doesn't really say much about what energy even is. To get an idea of what energy truly is, I think it's time I talk about its most important aspect, the law of conservation of energy. This means that energy can only be converted from one type of energy to another or be transferred somewhere else. Energy can't just pop out of nowhere or suddenly disappear. The total amount must remain constant. However, if the total energy remains the same, then this means that the amount of kinetic and potential energy is limited, and that's true. Because of this conservation law, we can say that energy is a measure of all the possible motions an object can have and all possible locations it can reach. Position and location are technically very fundamental when you think about it. In order for something to physically change, something needs to move, and moving changes position. Therefore, energy is a measure of the maximum amount of change that can happen. It sets a limit to the amount of motion an object can have and how much an object's position can change within a given time interval. This is very abstract, and to be honest, knowing what energy isn't very useful. The real reason people care about it is that it has amazing predictive power in addition to it being conserved. There are two main ways to transfer energy: work and/or heat. There's technically a third way, and that's by mass entering or exiting the system because the mass itself carries energy. I'll get into this more later. I'd also like to clear up a misconception. If you've ever heard that work and heat are energy, that's only half true. They're specifically energy transfer. This is in the same way that you can have a bus carrying people and characterize it by how many passengers it has, but the bus itself is not a person, it's a vehicle. Be careful with this analogy though. You can easily see a bus, but you can't measure work and heat directly itself. You can only indirectly calculate them by measuring how they affect the properties of the system. I've mentioned the term system a few times, but what exactly is it? In thermodynamics, a system is defined to be whatever you're trying to analyze, while the surroundings is anything outside of that. The boundary is what separates the two from each other. Keep in mind that this boundary doesn't have to be a literal physical wall. These concepts of system, boundary, and surroundings are abstract. In practice, we define something called a control volume and control surface. The control volume is literally just the system, as it is the space the system takes up. The control surface is the surface area of the control volume and is the boundary. There are three types of systems defined by if energy and/or mass can be transferred across the boundary. First is the isolated system. This is a type where nothing, neither energy nor mass, can be transferred across the boundary. Second is a closed system. This is where only energy can be transferred across, so no mass transfer. We often call this a control mass system. And third is the open system. This is where both mass and energy can be transferred across. We also often call this a control volume system. The terminology of control mass and control volume can be a bit confusing. They both have control volumes and control surfaces, but the difference is that in a control mass system, the control volume and surface conform to the shape of the mass, while for a control volume system, it doesn't have to. Anyway, so what is work and what is heat? To understand their behavior, it's important to remember that all objects are made up of particles. These particles have a lot of interactions with other particles in the system and the boundary of the system. These interactions are microscopic forces, by the way. For work, this is energy transfer due to macroscopic forces resulting in motion. What this means is that if you add up all the microscopic forces and average them, it results in a measurable macroscopic force. The energy transferred by work is overall very concentrated and more consistent. The important concept is that a majority of the particles in the system need to act in unison to achieve this macroscopic force. For heat, if you did the same thing of adding and averaging the microscopic forces, you'd get, well, nothing. Rather, something else would catch your attention: the temperature. Heat is energy transfer not due to macroscopic forces, or more specifically, it's caused by differences in temperature. It is capable of changing the temperature and phase of substances. It's important to note that the energy transferred by heat only goes from hot to cold, and it will continue to do so until the temperatures are the same. If you want to learn more about the nature of heat and work, and even the theoretical basis of thermodynamics, you'll have to look into something called statistical mechanics. I must warn though, it's a very difficult topic to understand, and so far I haven't found a video series that can explain it good enough. With that, how does energy transfer affect a system? The first law of thermodynamics is essentially the equation for the law of conservation of energy. It tells us how energy is converted from one form to another and where it goes. Earlier, I mentioned that there are two types of energy, kinetic and potential. However, a system can have a lot of particles. For instance, a single gram of water contains about 33.5 billion trillion H2O molecules. Tracking the energy of every particle is impractical due to the sheer number of them, so instead, we just condense it into a single term, the internal energy, du. That being said, the entire system can also have kinetic and potential energy, which is separated from the internal energy. For example, if a system moved to the right with a speed of 5 meters per second, then all particles inside will have that 5 meters per second plus their random motion. The 5 meter per second motion can be separated from the random motion of the particles, so the kinetic energy associated with that 5 meters per second is separated from the internal energy. The same logic can be applied to the potential energy. All in all, the total energy of a system is the sum of its internal energy, kinetic energy, and potential energy. So for any system we define, it has these three energies. By putting a d in front of the terms, we're expressing it as a small change or a small amount of its respective quantity. But in order for the system's energy to change, energy must be transferred into or out of the system. Therefore, we say that the total change in the energy of a system is the sum of the energy transfer due to heat, work, and mass transfer. The delta indicates a small amount of heat transfer or work done. When there isn't any mass transfer across the boundary, DEM equals 0, which applies to isolated and closed systems. You might wonder why we have two symbols, d and delta, both of which indicate differentials. The difference is that the amount of heat and work done depends on the process that a system undergoes. The energy of a system, however, doesn't depend on how things happen. It's literally just the embodiment of the properties of the system, so it only depends on its initial and final states. To notate quantities that depend on the process done, we use delta and call them path functions, while for those that only depend on the initial and final states, we use d and call them state functions. Say for example, you're trying to heat up a soup to a certain temperature. You could do this by putting the pot over a fire, or alternatively, you could use a pressure cooker. These two involve very different thermodynamic processes. The pot over the fire is a constant pressure or isobaric process, while the pressure cooker is a constant volume or isochoric process. To raise the temperature of the soup by the same amount, the isochoric process requires less heat than the isobaric process. The same goes for work. There are many processes to do work, and they're all not the same. For the mass energy entering or leaving the system, it has its own internal kinetic and potential energy. However, it also carries additional energy due to work being required to push mass into or out of the system. So it also includes something called flow work, notated as delta W flow, which is equal to dPV. In thermodynamics, we have a quantity called the enthalpy, H, and it is defined as the following. dH is equal to du plus dPV. From Bijus, they say that enthalpy describes the internal energy that is required to generate a system and the amount of energy that is required to make room for it by establishing its pressure and volume and displacing its environment. In concept, enthalpy is related to energy transfer due to mass transfer because the mass itself contains internal energy and work is required to push the mass into or out of the system. This results in the following expression for the mass energy entering the system. DEM is equal to DHM plus D kinetic energy M plus D potential energy M. To summarize everything, the first law of thermodynamics is the following. Delta Q minus delta W plus DEM is equal to DE cis, where DE cis is equal to DU cis plus DKE cis plus DPE cis, then DEM is equal to DHM plus DKEM plus DPEM, and DHM is equal to DUM plus delta W flow. You probably have noticed the negative sign in front of the term for work. This notation basically means that when work is positive, energy is being transferred out of the system. Oftentimes, especially in mechanical engineering, we're more concerned about how we can extract energy from systems, so yeah. It's confusing at first, but you kind of just get used to it. For all other quantities, if it goes into the system, it's positive. You can refer to the image and table on screen for the sign convention. Let's say I want to build a motor that takes in heat and moves the vehicle. Assume that there's some device that really just does that. So, by the first law of thermodynamics, we can set work and mass transfer to 0, and that the internal and potential energy of the car doesn't change. So there, heat converted into kinetic energy. Right? Oh, if only things could be so simple. We have to be a bit careful when we use the first law of thermodynamics. The conversion of heat to kinetic energy seems valid, but in reality, that's not what we observe. Heat alone is very terrible at making things move. I mean, seriously, try making something move by putting a fire over it. It doesn't really move that much. All it does is really change the temperature or phase of objects. So what gives? To efficiently increase the kinetic energy, we actually need work, not heat. Basically, what we want is to convert heat into work, and then from there you can actually just make the work do whatever you need it to do. Systems that do just that are called heat engines. In addition to converting heat to work, it should also operate on a cycle. What is a cycle, you ask? It's where a system returns to its initial state after undergoing a set of thermodynamic processes. If the engine didn't run on a cycle, there would be a point where the engine wouldn't be able to run anymore, even with a constant stream of heat being supplied, even assuming ideal conditions. However, with a cycle, it is guaranteed that the engine will always run so long as heat is supplied in ideal circumstances. When I say ideal circumstances, I'm basically saying that all the processes have no inefficiencies, and everything is practically perfect, so no friction, no dissipative forces, none of that. Which technically means that it's impossible, but even without ideal circumstances, it's much easier to keep a cycle running than it is to have one that doesn't operate on a cycle. Let's see how we can meet these two conditions. You might be familiar with the ideal gas law. This is one of the most important equations to, well, really ever exist, so it's best to remember it well. PV equals mRT, where P is the pressure, V is the volume, M is the mass, T is the absolute temperature, which is either Kelvin or Rankine, and R is the ideal gas constant, for a specific gas considered. For example, air has an R of 0.2871 kilojoules per kilogram Kelvin. You can also have other versions of it depending on if you're using a number of moles or particles, but this is the one I'll use. The important thing I want to point out is that raising the temperature increases the pressure when the volume is held constant, and vice versa. Likewise, raising the temperature with a constant pressure increases the volume, and vice versa. If you know anything about the gas laws, like Charles' law, Boyle's law, Gay-Lussac's law, it's basically those relationships if you want to learn more about it. In fact, the ideal gas law is basically just the condensed version of all those three laws. There's also another one, like Avogadro's law, but again, ideal gas law is the embodiment of all of them. Anyway, we can take advantage of this behavior by making use of a slider crank mechanism. This converts oscillating translational motion into rotational motion, which is exactly what we need. The slider here will be a piston, and there will be a cylindrical enclosure around it with one end open. This open end is where the piston can move inward and outward along. Lastly, inside the cylinder is a gas. Let's assume that the piston is currently at the top dead center. What we need to do is to increase the pressure of the gas so that it pushes the piston down, turning the crank. By adding heat, the temperature increases, which also increases the pressure. Because the gas now has a higher pressure, this overcomes the pressure that was applied by the piston, which then pushes it down to the bottom dead center position, meaning that the gas does work on the piston. Now we need to bring the piston back up. However, the gas is hot and has a high pressure, which makes it really difficult for the piston to compress the gas. Basically, if we compress it now, we would get very little work output, or basically the same amount of work would be required to push it back downward. But what we can do is to decrease the temperature of the air, so heat must be rejected out of the gas and to the surroundings. This reduces the pressure of the gas, allowing the piston to much more easily compress, and then it moves it back up to the top dead center. I'm glossing over a lot of details here, but I'll get into that later. All we have to do is to continue to add and remove heat from the gas to keep the crank turning. This creates a thermodynamic cycle. Unfortunately, there's an unavoidable price to pay because we need it to run on a cycle. If you calculate the heat input and compare that with the net work output, you might find something strange. Even if you use the most optimal heat engine, you cannot convert 100% of the heat added to a net work output, even theoretically with ideal circumstances. This says you always need to remove heat from the system no matter what. But that begs the question, why? There are a lot of thermodynamic processes that exist, so who's to say that there isn't one process that could, in theory, bring a system back to its original state without removing heat? Let's think about it. In order to efficiently push down the piston head, the gas particles need to move downward and collide with the piston head. Now, to do work, the particles need to behave in a collective ordered manner. However, the motion of particles is essentially random. In reality, it is much more likely for the particles to hit the walls of the cylinder and other particles, and not the thing we want them to hit, which is the piston head. This randomness is what limits the thermal efficiency of heat engines. In addition, there are other inefficiencies like friction. The piston head does slide against the cylinder walls, so that does create friction, which also releases heat. I've been going on and on about thermodynamics, but I've barely even touched on the motorcycle. Well, your patience has finally paid off. Let's now put everything together. Earlier, I described how you can expand and contract a gas by heating it up and cooling it down. But I left out some important details. To heat up the gas, we use combustion. Basically, combustion is a chemical reaction where you add a little bit of heat to fuel and oxygen, which releases even more heat, among other byproducts. In order for a combustion reaction to occur, 3 components are needed: oxygen, fuel, and a little heat. First up is oxygen. This requirement is pretty easy to meet as air is all around you and contains oxygen. Air has approximately 79% nitrogen and 21% oxygen by volume. But in terms of mass, it is 77% nitrogen and 23% oxygen. Technically, there are other components to air, but they're mostly nitrogen and oxygen. We do have a problem though. After combustion, very little oxygen will be left in the cylinder, and the air is also very hot. To tackle both of these problems, the air in the cylinder is just exhausted out, and we let the ambient air cool it down. Of course, this gives rise to another problem. There's no more air in the cylinder. Well, luckily, this is solved by adding an additional step where we need to pull new, cool, fresh air into the cylinder. To control the flow of air into and out of the cylinder, we'll make use of 2 valves, one for the intake and one for the exhaust. The second necessity for combustion is fuel. Gasoline doesn't seem to exist in Teyvat, or at least as far as we know. However, it is pretty obvious that the fuel Mavuika's motorcycle runs on is phlogiston. In real life, there was something called phlogiston theory, but it wasn't really a fuel. You can learn more about phlogiston from crash courses The New Chemistry, Crash Course History of Science number 18, or alternatively, you can watch How This Impossible Theory Led to the Discovery of Oxygen by Chemistorian. Whatever the case, phlogiston is the fuel of the Flamestrider. For motor vehicles, liquid fuels are the most convenient in comparison to solid and gaseous fuels. Many years ago, steam locomotive trains would use coal, which is a solid fuel. However, those need a large storage to have enough fuel for a long journey. In addition, injecting consistent amounts of a solid material with irregular shapes and sizes into the cylinder is going to be very difficult. For gas fuels, they tend to have a lower energy density in comparison to liquid fuels, meaning that the fuel tank would either have to be pressurized or be larger. So the type of fuel required for the Flamestrider would specifically have to be liquid phlogiston. Now for the third and final requirement of combustion. We need a small bit of heat to jumpstart the reaction. With actual gasoline engines, they have a component called a spark plug inside the cylinder. Basically, it creates an electric arc, thus triggering the ignition. If you have a gas stove, that clicking sound you hear is actually the sound of an electric arc. Hold on. Electricity and fire, electro and pyro— Hey, wait a minute! That's an overloaded reaction! Combustion is pretty much an explosion, so overloaded also fits since it's shown to be quite explosive. But there's just one teensy little problem. We're not dealing with electro and pyro, we have phlogiston. The electro can be supplied by devices, and I don't think it's a stretch to say that there are devices in Teyvat that can create electro. It is, at this moment, I started to wonder, would applying electro to phlogiston trigger overloaded? So I decided to ask what others think about phlogiston. Thank you to Keef554, Wildest Winters, Squilladog, Talking Cow that was there all along, this Hard5697 on YouTube, and thank you to Sashimi/Loki and Talking Cow that was there all along for discussing with me on Discord. You're all amazing, and thank you for your input on trying to help me understand phlogiston. I even held a vote, which gave me these results. Yeah, okay, so the majority of people seem to think that phlogiston doesn't react with electro, but do keep in mind, majority opinion does not necessarily mean accurate. Either way, I ultimately decided I would just try to find a way for how things would work, assuming there was no reaction between phlogiston and electro. Talking Cow that was there all along and I spoke on Discord, and eventually he gave me just enough lore tidbits to the point where I could actually see how things might work. In Act 4 of the Natlan Archon Quest, you can speak to the Lord of the Night and ask about elemental energy. The Lord of the Night says this.
You come to me with many questions, and you should be rewarded for your bravery. Ask, and you shall have the knowledge you seek. Phlogiston is Teyvat's primordial form of energy. The heavenly principles used phlogiston as a basis for the creation of elemental energy, to develop a power to better counter the abyss.
The important takeaway is that phlogiston can be converted into the 7 elements. For our case in particular, we can actually supply both electro and pyro just from phlogiston alone, which is pretty cool. In actual engines, an external battery is needed for the spark plug. Exactly how phlogiston can be converted into the elements is currently unknown, but the given explanation we have for it is this.
Have you heard of the concepts of the light realm and the human realm? That explanation might take too long. Light refracts into 7 different colors, which we collectively refer to as a rainbow. Elemental energy is a similar concept. It's essentially the modern counterpart of phlogiston.
Yeah, it's not really enough information, but luckily for us, it turns out that we don't need to know how the conversion works, because there are already devices in Teyvat that can do it for us. Once you've reached Friendship Level 4 for Mavuika and completed Incandescent Ode of Resurrection, you unlock a section on the Flamestrider and it says this. Thus, Mavuika and Lunan joined forces to delve into the secrets behind the source mechanisms. The solution, then, was to use modern smithing techniques to create said parts independently and combine the 2 elements. A process that involved lots of overheating and explosions, en route to solving the pyro compatibility issue that the source mechanisms had. Whatever these source mechanisms are, it seems that with a bit of modification, they can be made compatible with pyro and were used in the Flamestrider. Notably, the researching and prototyping phase involved a lot of explosions. Might I remind you that the overloaded reaction in particular is explosive, being powerful enough to knock back anything near it. Perhaps what's needed in order to make the source mechanisms compatible with pyro was to modify them so that they can convert phlogiston into electro. So what exactly are these source mechanisms? Well, I actually think we're well acquainted with this technology, the secret source automatons. Just from its name, the term source is there, it's pretty reasonable to suggest that they are machines built out of these source mechanisms. In addition, if we look at the source mechanisms around Ochka Natlan, they share similar geometry to the secret source automatons. As of version 5.3, there are only two types of secret source automatons, the Hunter-Seeker and the configuration device. If you take a close look at them, you'll find the same orange, yellow, blue, and red coloration associated with phlogiston, so we can certainly say that they're powered by it, or just use it in some capacity. If we observe them in combat, we'll notice something interesting. The Hunter-Seekers deal damage to you with pyro attacks, while the configuration device attacks you with electro. Those are the exact elements needed to get the motorcycle to run. With all the lore puzzle pieces in place, I think we have a pretty good idea for how the Flamestrider works in the universe of Genshin Impact, and hopefully from a physics and engineering perspective as well. Let's now take all that we know and come up with an explanation. For traditional motor vehicles, they operate based on either the Otto or diesel cycle, both of which are thermodynamic cycles that can be used for heat engines. Gasoline engines use the Otto cycle while diesel engines operate on the diesel cycle. In motorcycles, gasoline engines are a lot more common, so I'll just assume that the Flamestrider also runs on the Otto cycle. Let me define the system to be the mass of mixture contained inside the cylinder bounded by the walls and the piston head. Note that because the piston head can move inward and outward, the control volume can decrease and increase. It's also worth mentioning that the system can be open or closed. When the intake or exhaust valve is open, the system behaves as an open system. However, when they're both closed, it's a closed system. To visually understand how the system evolves, on screen is a pressure versus volume or PV diagram of the 4-stroke Otto Cycle. Every point on the graph corresponds to a specific pressure and volume the air inside the cylinder may have at any moment throughout the cycle, and every path between 2 points corresponds to a specific thermodynamic process. There are 3 processes involved: isobaric, isochoric, and isentropic. Isobaric simply means constant pressure. Isochoric is constant volume, and isentropic is constant entropy. Entropy is another quantity that is extremely difficult to conceptually understand and would be worth its own video. Just know that in an isentropic process, none of the work done is converted into heat. With all that said, this is how Mavuika's motorcycle would work in the context of Genshin Impact. From process 0 to 1, the system undergoes isobaric mass intake. The intake valve opens and the piston moves downward from its highest point, also known as the top dead center. Due to the lack of air inside and the increasing volume, this generates a vacuum pressure, sucking new, fresh air into the cylinder. Because air is allowed to enter the system, it currently acts as an open system. Simultaneously, liquid phlogiston inside a fuel tank is supplied to a source mechanism via a pump that converts it into electro. This electro element is then injected into the cylinder, resulting in an air-fuel mixture. Once the piston reaches its lowest point, also known as the bottom dead center, the intake valve closes, where it becomes a closed system. From process 1 to 2, the system undergoes isentropic compression. The piston pushes into the cylinder, compressing the air until it reaches the top dead center. Due to the compression process, the piston does work on the air-fuel mixture, increasing the pressure. For process 2 to 3, the system undergoes isochoric heat addition. A second pump supplies liquid phlogiston into another source mechanism, which converts it into pyro. From here, the pyro element is injected into the cylinder, and because it contains electro, an overloaded reaction is triggered. This releases a lot of heat, which is then absorbed by the air, increasing its temperature and pressure even further. From 3 to 4, the system undergoes isentropic expansion. The air does work on the piston, pushing it down with a high pressure until it reaches the bottom dead center. From 4 to 1, the system undergoes isochoric heat rejection. The exhaust valve opens, quickly dropping the pressure inside the cylinder. This reduction in pressure reduces the temperature of the air, meaning the heat is rejected out of it. Opening the exhaust valve also makes the system become an open system again. And lastly, from 1 to 0, the system undergoes isobaric mass exhaust. The piston moves upward, pushing air out of the cylinder through the exhaust valve. Once the piston reaches the top dead center, the exhaust valve closes, and from here, the whole thing continues to repeat itself back from the intake process. You might also commonly hear that the 4-stroke engine is described based on, well, its 4 strokes: intake, compression, power, and exhaust. The intake stroke is process 0 to 1, the compression stroke is 1 to 2, the power stroke is from 3 to 4, and lastly the exhaust stroke is from 1 to 0. For 2 to 3 and 4 to 1, the piston doesn't move at those points, at least ideally and theoretically, so they aren't really part of any stroke in particular. Now, to put things back into reality, an actual gasoline engine obviously doesn't have any source mechanisms or phlogiston. A fuel pump will inject the fuel into the cylinder during the isobaric intake process. Then during the isochoric heat addition process, the spark plug creates an electric arc which triggers the combustion reaction. And in order for the spark plug to operate, it has to be connected to a battery. This is different to my proposed explanation for the Flamestrider, since phlogiston is the only source of power involved in the combustion. There could still be a battery in the Flamestrider. After all, the phlogiston pumps need some sort of power source. It's just that the electricity provided by the battery isn't used to trigger the overloaded reaction. This design unfortunately does mean that the Flamestrider would have a lower mileage, since more fuel, the liquid phlogiston, would be consumed in, well, being used as the fuel for its combustion, and for its own trigger. Another difference is that in an actual gasoline engine, fuel is supplied into the cylinder during intake, then on the power stroke, an electric arc ignites the fuel. This is in contrast to the Flamestrider, which has electro injected first, then pyro later. The reason why is because putting pyro into the cylinder first would heat up the air, causing the system's temperature and pressure to increase. This would further increase the work of compression, reducing the net work output and decreasing the overall thermal efficiency. For one last minor detail, this process only describes the engine during operation. How do you get it to start, and how do you get it to stop? Well, to start the engine, what you have to do is spin the crankshaft fast enough until the engine can maintain itself. With some of the oldest cars, people would use a hand crank to manually spin it, but obviously that's very tiresome. In the modern day, and for Mavuika's motorcycle, an engine starter is used, which has an electric motor to spin the crankshaft. And finally, to stop the engine, all we need to do is to disconnect power from all the components involved in combustion. For the Flamestrider, power would have to be disconnected from the liquid phlogiston pumps. If the pumps aren't on, they won't be able to supply phlogiston to the source mechanisms. Then no pyro and electro can be made. Therefore, no overloaded reaction would be triggered. To recap, I first talked about energy and the basics of thermodynamics. After that, I showed how we can take advantage of how gases respond to heat transfer to create heat engines. From there, I gave an overview of the requirements for combustion and how those requirements could be met in Genshin. Lastly, I incorporated everything together, explaining the operation of the 4-stroke ideal Otto Cycle to explain the process of how the Flamestrider's engine operates. It's cool and all to know how the engine works, but there's a lot left to explain. This doesn't explain how the rotation from the crankshaft spins the wheels, how it can float on water or liquid phlogiston, and how it can fly. In addition, there are other things that I would like to look at, such as figuring out how much horsepower Mavuika's motorcycle has, as well as the physics of her drifting. Judging by the length of this video, I'll have to save those for another time. In any case, be sure to subscribe so that you won't miss out on those, and while you're at it, you can like and share the video or support the channel via super thanks or channel memberships. If you find engineering interesting, I have a recommendation for you guys. My first Genshineering episode flopped pretty hard even though it was the most effort I ever put into a Genshin video. If you could watch it, I express my gratitude. Lastly, thanks to everyone who tried helping me understand phlogiston, and to Talking Cow that was there all along for helping me conceptualize how I should explain heat engines, particularly the heat-to-work conversion inefficiency. So, yeah. That's really about it for now, so thanks for watching and hope you've enjoyed.